Hi, I'm Jenna, and I'm going to be talking about the suprachiasmatic nucleus, which is the smallest but most powerful part of the brain, and the most interesting, in my opinion. It's basically the CEO of our body's 24-hour schedule. So, firstly, what is the SCN? Well, the suprachiasmatic nucleus is this tiny cluster of about 20,000 neurons, and it's located in the hypothalamus. And even though it's so small, it serves as our brain's master clock. It's above the optic chiasm, so it's past like our optic nerves from where our eyes are, and that's because of the way that the sun and like light plays into it, which I'll talk about a little bit more later. But it sits in the hypothalamus and controls our circadian rhythms, which is like sleep, alertness, hormone releases, body temperature, and even like our eating patterns. So, where it sits and why it matters, this is kind of a diagram of showing where exactly it is. And the name itself actually like kind of gives us an understanding of where it is. So, supra means above, and then chiasmatic is from the optic chiasm. So that's why it's called the suprachiasmatic because it's above the optic chiasm. Um, and you can see it like over here. That's where the light enters our eye, and then that's where the SCN is above there in our hypothalamus. It coordinates timing across our whole body, and it's in like the perfect position to receive light information since it's right above the optic chiasm. And since it's like right where those optic nerves cross, it allows the SCN to get the direct information about the light, which is the most important part of the signaling to keep our internal rhythms on track. And then this is a little bit about how it actually keeps the time because we can say a lot about how it like it takes all the light and everything, but we can't really like fully understand it. And I mean even how much I'm going to be describing it isn't going to be like a full complete level of understanding just because there is so much that plays into it as far as like hormones and like the monomers and polymers that are involved in the release and transmission of those neurotransmitters. But um, the basics of it is this kind of picture shows the fluctuations of different hormones um, that are being released during like throughout time. I'm trying to I don't know if you can really see, but like this is one kind of hormone. Like each one is a different hormone, and they rise in the morning and fall at night, whereas other ones like are lower in the morning and are higher at night. Um, and it uses what's called like clock genes, and these are those clock genes, and they turn on and off in like this rhythmic cycle, and it lasts. The cycle is a little bit more than 24 hours. Um, and even if you put like our SCN in total darkness, those cycles would keep going, which is why it can maintain its own rhythm without any outside cues. But the light plays into that. So that's why when our light is like off of what we're actually sleeping and doing, it like kind of messes with our body. And I'll talk a little bit more about that and how that plays into like jet lag or night shift workers and stuff like that. But so our internal clock genes are also what's helping regulate that rhythm, and those like fall and rise daily. And then here's a little bit more about how the light plays into this. Obviously, our lives don't happen in complete darkness, and light is the number one thing that resets the SCN each day. So we have special cells in our retinas that detect light, and those send information straight to our SCN through something called the retinohypothalamic tract. And every morning, sunlight basically taps on the SCN on the shoulder and says, like, "Hey, it's time to start the day." But the morning light is the strongest Zeitberger, or like the Zeitgerber is like the indication that kind of indicates that it's like awake time, if that makes sense. So that's why the morning light would be the strongest, because that's like when the sunlight is the strongest and it's the most contrasting to the darkness that we were in before. And then our retinal ganglion cells detect that light, and it goes through that pathway, and it adjusts our entire internal schedule. That's also why like blue light glasses and things like that are so important, because um, the light that comes from our devices, like our computers or phones or tablets or whatever, those like are kind of absorbed in our brain the same way that sunlight would be because of that blue light. which is why people say like don't be up on your phone an hour before you go to sleep, because that can throw off your circadian rhythm, because when your brain is detecting that light, it kind of makes it think like, oh, it's daytime, it's time to be awake. But we know that now that we have those kinds of devices and things, that kind of throws it off. So that's why you see a lot more people now wearing blue light glasses or doing other things to try and, prevent the mixing of the blue light from our devices from our actual circadian rhythms and prevent that from like throwing us off. But that diagram kind of shows where the light enters and how that pathway goes about. And then that's another picture that just shows the other kinds of things that can go into our eyes that are registered as blue light the same way that sunlight is. And then this is a little bit about the pathway that takes it to the pineal gland. Um, One of the biggest jobs of the SCN is to control melatonin, which is the hormone that makes us sleepy. I know everyone probably knows what melatonin is because we take, like, when you haven't been going to bed at the right time for a long time and then you have to wake up early the next morning, you take melatonin to make yourself go to sleep a little earlier. But during the day when there's light, the SCN blocks the melatonin release. And when it gets dark, the SCN signals to the pineal gland to start releasing the melatonin, which is why when we take melatonin, that's why we would like go to sleep sooner, because since it's being released, it'll signal the pineal gland to release more. And that can make us go to sleep. But I believe melatonin only allows us to sleep about like half an hour earlier, just because it's not like a lot of it. But even just that little push can help our body like get back into the rhythm of things, which is why people usually use it. But it signals our body that it's time to sleep. Oh, and I accidentally put that twice, but that's fine. Yeah, and the darkness is what kind of helps us to know that it's time for that to be released. And then that's just a picture that shows the cycle of our hormones throughout the day and how melatonin is released at nighttime. And then as far as like the behaviors that the SCN regulates, which is, in my opinion, the most important and most interesting part of it, just because like sleep is obviously very important, but what's more interesting is the things that happen when our sleep schedules are off and the way people react when they're low on sleep. And we see it all the time. Like if you don't get a lot of sleep, you're very irritable, or like it kind of throws off your whole day. I know for me, when I wake up earlier than I usually do, I can't eat in the mornings, or it just like kind of throws my whole body off and I don't feel right. So it's it goes a lot beyond sleep, and it regulates our cortisol, which peaks in the morning to help us feel like most alert, and it helps like set the rhythm for our body temperature, feeding cycles, mood, and just like our overall energy levels throughout the day. So basically, if your behavior changes based on the time of day, which almost all behavior does, it's from the SCN doing its work to control that. So our sleep wake rhythm, our cortisol timing, our body temperature, our mood, attention, alertness, like all of those things are controlled by the SCN overall. Obviously, it goes through those pathways, alerts the pineal gland, goes through all the pathways it needs to go through to make those things happen. But overall, the SCN is pretty much the one that controls all those things. And then here's another graph that just kind of shows our level of alertness over time and how we peak. Most people peak alertness like in the morning. And that's just because of like our circadian rhythms and how our cortisol peaks in the morning. And then now we can talk about like what happens when that gets disrupted, because I think that plays a little bit more into it. So when it gets thrown off, like we really feel it. Like jet lag is a really big thing. I'm sure like if you've ever experienced that, you know exactly what it feels like. It happens like when the external world suddenly shifts, but our SCN doesn't shift that suddenly. So like if we go on a plane, our bodies like we it doesn't move as fast as going across an ocean would if you're on a plane. So our bodies adjust a lot slower, which can cause it to be like mismatched with the external environment, which is why it causes us to be like so much sleepier or feel like we're on the wrong schedule. The same thing is true for like night shift workers. There's like a chronic circadian misalignment, and I am one of those people. I work night shift, and it feels like a twilight zone, because you go to work and you come home and then you sleep until like 3 p.m. I wake up and then I feel like 2 hours later I'm going back to work. But it kind of shifts everything, because then when I'm back at school and I'm like doing classes and everything, I still go to bed super late. It's still really hard for me to wake up early in the morning, because it's like all misaligned all the time. And since like people who work night shift, since they're chronically doing that, our circadian rhythms are never aligned with like the lighting outside, like the sunlight, the blue light that we were talking about. Our cortisol levels do not peak like the same time that others would. And it kind of is constantly like fighting with our what our internal clock wants to do and then what we're actually doing. Um, and in animal studies, when researchers damage the SCN, the animals completely lose their circadian rhythms. Like they sleep, eat, and move just at completely random times. So that can cause like a lot of problems, like metabolic changes, mood issues, fatigue, which is why night shift workers are often paid more to make up for that, because studies also show that like over time it can lead to shorter lifespans. Um, yeah, and then like obviously that kind of plays into how those studies with the SCN lesions, they don't end up having a circadian rhythm at all. Um, and then just a little bit about like daily life examples, like how morning sunlight helps set our clock. Like that's why we like to wake up and open our blinds, or how staying up late delays our rhythm and we feel a lot groggier in the morning, or how pulling up all nighters can cause our rhythm to be fragmented, and that's why you shouldn't do that before an exam, and that phones and blue light can really like confuse our SCN and kind of make that a little bit more difficult to fall asleep. Uh, I chose this because as a night shift person, I find it very interesting because I definitely feel those differences. And I just think that it's a really like small but very influential part of our brain. It deals with like so many parts of our mood, like our sleep, our mood, our stress, our metabolism. It shows up in how we eat, how we behave with others, and it's still connected to like those neurotransmitters and biological perspectives of it. So I find that super interesting. And I think that understanding it can kind of help us improve our daily life. Maybe not if we're still working night shift, but when I'm not, it helps me know like I should definitely go to sleep by this time so that I feel better in the morning, and stuff like that. So I just think it's super interesting, and I hope you do too. Thank you.